Hi everyone, welcome to my channel Chemistry Tutorials by Kiranmai. And today's topic is filling of orbitals in atom. Filling of orbitals in atom means we are going to discuss about filling of electrons into the orbitals in atom. Filling of electrons into the orbitals in atom takes place according to Aufpuff principle. Aufpuff is a German word which means building up. Building up of electrons means filling orbitals with electrons. So we all know that we have a nucleus in an atom and this nucleus is surrounded by electrons. And now we are going to discuss about how electrons are filling in the each orbital. Orbital is nothing but the imaginary space around the nucleus where the probability of finding the electron is maximum. So here electrons will be filled according to this Aufpuff principle. This principle is mainly based on Pauli's exclusion principle, Hund's rule of maximum multiplicity and relative energies of the orbitals. First, we are going to discuss about Aufpuff principle. According to Aufpuff principle, in the ground state of the atom, the orbitals are filled in order of their increasing energies. We have to remember that in ground state of the atoms, when an atom is stable or when it is not reacting with another atom, ground state, the term ground state is usually referred. We will be discussing in further classes what is meant by ground state, what is meant by excited state and all. Excited state means when we provide an energy, electrons get excited and move into higher energy orbital, and that state is referred to as an excited state. But when the atom is in neutral state, it is referred to as ground state. In this ground state, the orbitals are filled in the order of their increasing energies. Means first lower energy orbitals are filled and then the higher energy orbitals are filled. Electrons first occupy the lowest energy orbital available to them and enter into higher energy orbitals only after filling lower energy orbitals. For suppose, if we consider this as an increasing energy order and this one is lower energy orbital and this one as higher energy orbital, first electrons get occupied or first electrons fill lower energy orbital and then it move into higher energy orbital. So first electron fill lower energy orbital and then it moves into higher energy orbital. Before filling lower energy orbitals, electrons will not move into higher energy orbital. There is no single ordering of energies of orbitals which will be universally correct. See here, we said ordering of energies of orbitals means which orbital is lower energy orbital, which one is higher energy orbital. To specify this, which one is lower, which one is higher, there is no specific order. But however, this order is useful. Just remember this order: 1s, 2s, 2p, 3s, 3p, 4s, 4p, 5s, 4d, 5p, 4f, 5d, 6p, 7s. So this order must be remembered. Here this order is not an exact order in which electrons are filled in the orbitals. However, most of the atoms fill in most of the electronic configurations while we are writing use this order. There are few exceptions, but most of the atoms follow this order. In most of the atoms will follow this order in filling of their electrons. To remember this, just write down 1s from 1s, s orbit 1s, 2s, 3s, 4s, like that. And then in the second row, start from 2p, 3p, 4p and all. And then the next third row, start from 3d and next one 4f. Why we have to start from 2p and why there is no 1p orbital means I will discuss that one in the later part of this video. For now, just remember this order: 1s, 2s, 3s and all, and then from 2p and then from 3d and then from 4f. Start from the right top of the corner and then draw an arrow mark to left bottom and follow these arrow marks to remember the order of energies of orbitals. Most of the cases this will be the order. So first electrons fill 1s orbital and then it comes to 2s and then it comes to 2p and then 3s, next 3p and then 4s, next 3d and then 4p and then 5s. So in this order electrons are filled in the orbitals. So we can say that 1s orbital is lower energy orbital than 2s and 2s is lower energy orbital than 2p. So first lower energy orbitals get filled and then higher energy orbitals are filled. There are few exceptions. For example, chromium. Chromium atomic number is 24. And then if we write the electronic configuration, expected configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. But in this chromium atom, the actual electronic configuration will be as 1s2, 2s2, 2p6, 3s2, 3p6, but 4s1, 3d5. See here, expected configuration is 4s2, 3d4, but actual configuration is 4s1, 3d5. Why we are writing this one means due to several reasons. Why? Because 4s and 3d5 are half-filled orbitals. So s orbital can occupy 2 electrons. So half-filled means 1 electron. And d orbital can occupy 10 electrons. So d subshell can occupy 10 electrons. Here it is 5, means half-filled. This half-filled configuration gives more stability to atoms. So to attain this half-filled configuration, electron move from s orbital to d orbital, and the energy gap also between 4s and 3d, the energy difference between 4s and 3d orbital is also low. So this is also the reason to the configuration 4s1 and 3d5. So most of the cases the energy ordering of energies of orbitals will be in this order. Next one, Pauli's exclusive principle. According to Pauli's exclusive principle, no two electrons in an atom can have the same set of 4 quantum numbers. So we all know that quantum numbers gives the address of electron, means in which shell it is, in which subshell it is, in which orbital the electron is present, and in which orientation, means whether it is spinning clockwise or anti-clockwise, and all. We'll get the information from these quantum numbers. You can also check my video quantum numbers. I will give the link in the description box to know more about these quantum numbers. Okay. So according to Pauli's exclusion principle, no two electrons will have the same set of 4 quantum numbers. We can say that as we have a fingerprints, each individual will have specific fingerprints. Electrons will also have specific quantum number. So one electron will have specific quantum number which differs from the other electron. Suppose, let's see, we are comparing electrons present in pz orbital. It may have same principal quantum number, means which shell it is, 3 shell. So same p subshell from azimuthal quantum number will get the subshell, which subshell it is, and pz from magnetic quantum number will get which orbital it is present. And spin quantum number, if we compare spin quantum number for the electron present in pz orbital, one will have plus half and another one will have minus half, means it will not have exact same quantum number. Both electrons will not have same quantum number. They may have same principal quantum number, same azimuthal quantum number, same magnetic quantum number, but they differ in spin quantum number. So we cannot compare, means we cannot give 4 quantum numbers same for 2 electrons. Next, only 2 electrons may exist in the same orbital and these electrons must have opposite spins. So only 2 electrons will exist in one orbital. pz orbitals means they'll have only 2 electrons, but these 2 electrons will have opposite spins. So why this information is important means, with this information we can calculate the capacity of electrons present in any subshell. See, the maximum number of electrons in the shell with quantum number n is equal to 2n square. Let's see. For S subshell, azimuthal quantum number L equal to 0. By using this azimuthal quantum number, we can calculate magnetic quantum number, means number of orbitals present in subshell, 2L plus 1. So by substituting L value 0 in this formula, we get 2 into 0 plus 1 equal to 1. Means S subshell can have 2 electrons. So each orbitals have 2 electrons. So one orbital, so 1 into 2 gives 2 electrons. Similarly, for P subshell, if we calculate how many orbitals will be there, means L equal to 1. So substituting L value in this formula, 2L plus 1, 2 into 1 plus 1 means 2 plus 1, 3. So 3 orbitals will be there. Each orbital will have 2 electrons. So 3 orbitals will have 3 into 2, 6 electrons. So similarly for D subshell, we'll get 5 orbitals and 5 into 2, 10 electrons. See, for N shell, we'll have 2n square electrons. N shell means, for suppose we are taking one shell. If we substitute this one, we'll have 2 electrons. 2 into 1 square, 2 electrons. So one shell will have only one S2. So same thing as I said earlier, why we are not having 1p means one shell, principal quantum number 1 will have only 2 electrons. So it will be occupied by the s orbital. Then so there will be no 1p orbital or 1d orbital or 1f orbital. Similarly, for 2 shell will have 2n square, means totally 8 electrons. It will be like 2s square and 2p6. So there will be no 2d orbitals. As we mentioned here, there will be no 2d orbitals. So similarly, 3 shell will have 2n square, means 2 into 3 square, 18 electrons. They are as follows: 3s2, 3p6, 3d, 10. So Pauli's exclusion principle gives us the maximum number of electrons in the shell with principal quantum number n. So with principal quantum number n, the shell will have 2n square electrons. Next one, Hund's rule of maximum multiplicity. This Hund's rule of maximum multiplicity explains filling of electrons into orbitals belonging to same subshell. We all know that we discussed about Aufpuff principle. In Aufpuff principle, we said that lower energy orbital fills first and then higher energy orbital. And in Pauli's exclusion principle, we discussed that each orbital will have only 2 electrons. And here we are discussing about this orbitals belonging to same subshell. Means, for suppose, we'll have p subshell. P subshell will have 3 orbitals. P subshell will have 3 orbitals: px, py, pz. So p orbital will have three suborbitals: px, py and pz. In these suborbitals, how electrons are going to be filled? This one we are going to discuss in Hund's rule. Pairing of electrons in the orbitals belonging to the same subshell does not take place until each orbital belonging to that subshell has got 1 electron each, that is, it is singly occupied. This means if we take p orbital, if we consider p orbital, we'll have px and then py and then pz. So px, py and pz. The electrons must enter into px orbital, py orbital, pz orbital first, and then this electron should pair up. First it should be singly occupied, means each orbital must be filled with maximum 2 electrons. So before filling up of the other suborbital singly, it will not get paired up. I am explaining again. If the electron comes into px orbital first, the second electron must go into either pz orbital or py orbital. If px, py, pz orbitals are all filled with 1 electron, then the coming 4th electron will get paired up with the electron present either in px orbital, py orbital or pz orbital. Next. 1 electron goes into each orbital until all of them are half full before pairing up. See here. If we consider p orbital, px, py, pz must be half full, means it must have each electron in each orbital, and then only the electron can pair up. Let us discuss with some examples. If we want to write an electronic configuration for p2 orbital, suppose for p2, we cannot write px2, py0, pz0. Why? Because here the pairing up of electron is seen. This is not allowed. First electron should move with the other same orbitals, After half filling of same orbitals, then it is allowed to pair. So the configuration will be px1, py1, pz0. Next for p3, here also we cannot write pairing up. So we have to write as px1, py1, pz1. For p4, here px1, py1, pz1 and the fourth electron may enter into px or py or pz. So for convenience we are writing px2, py1, pz1, but we cannot write px2, py2, pz0. So according to Hund's rule of maximum multiplicity, the electrons must be the electrons must fill all the orbitals present in the same subshell first, and then it should start pairing up. So this is Hund's rule of maximum multiplicity. Thank you. If you like this video, share this video with your friends. Thank you.